And then we had the inner automorphism of the Lie algebra G contained in here. These I could view as a form at G, where G is in G. That's not the way of look of inner automorphism. This then was isomorphic to G, not the center of G, because that's the kernel of the adjoint. And then the corresponding Lie algebras were what we call derivations in G. And in here we had the inner derivations, which we could write in the form at x, where x lies in G. So that was the Lie algebra of this of int G. And then we showed that this was normal, and this was an ideal. So that was some of the work that we discussed for automorphisms. And so since this is normal in G, it's tempting to look at out G, mod int G. And say this is a Lie group with Lie algebra. The quotient of the ideals, right? Derivations, mod Rx. The problem is in this generality it's not quite true, because the question is this group here closed inside this group or not? And this was a problem that I think you raised. This is not clear. Remember, one way of defining this group was here. It's a connected subgroup out G with this Lie algebra, with the Lie algebra, the inner derivations. Right? This is an ideal in here. So there's some connected subgroup with this Lie algebra. We call it int G. Then show it has this form also. So when you say take a subalgebra and a Lie algebra, look at the connected subgroup corresponding to the subalgebra, it may not be closed. We don't know. Right? So in this, in generality, this may not be true. So that statement I made here is not correct. Unless you know int G is closed and out G, sometimes you know and sometimes you don't. Then there was an exercise we tried to do last Friday, which I want everyone to think about maybe, which was that if the center of G is trivial, then what's the first thing I can say? Well, so notice that this Lie algebra here, that this are all at x's. When is that 0? If and only if x lies in the center, right? So I can view this as G divided by the center of G. So the center of G is trivial. At x is this Lie algebra is just G itself. And what does that say? See, what the exercise was, let me just say it again, was that the center of int G is trivial. Okay, so certainly one thing is clear, which I think we discussed a little bit. If the center, what is the Lie algebra of the center? I claim it's just the center of G, so that's easy to see, which we know is trivial. So it means that the Lie algebra of the center of this group is trivial, which means the center is discrete. So this implies center of int G is discrete. So now the problem is trivial. Not only is it discrete, and nothing in there which is the center, right? So that's was a problem we didn't discuss last Friday. Second problem that we got stuck with a little bit was we said, well, if G has a real form, this implies that G and G bar are isomorphic. So that was the easy part. And the question, does a converse hold? Right? If G is isomorphic to G bar, does a converse hold? And we tried that a little bit on Friday and got stuck. So plainly the answer is no. And you should show that among the examples in exercise 2, they're counterexamples. So maybe I won't. So these examples we discussed on Friday. So they were a complex Lie algebra, and we showed that it depended on parameter A, and we showed that it was isomorphic to E bar if and only if A was real or length of A was equal to 1, something like this. Right. And I claim among those you should try to find one which doesn't have a real form when A is complex. So go back to this problem here, which is in the last section, the first chapter, where I talk about complexifications and try to find a counterexample to this. There was another problem we had on Friday. What was that? Something we didn't finish. Does anyone remember?
SPN is connected.
What was it?
SPN is connected.
Ah, yes.
But we can do this in another way.
Okay, how do you do it?
Using that proposition, if you have a Lie subgroup inside a Lie group, and this Lie subgroup is connected, and the quotient is connected, so the group is connected.
Okay.
And we can use the action of SPN on the spheres and argue by induction.
Ah, very good point, yes. So we saw this, that this is the same thing as S for n minus 1, and then use induction. We knew that SP1 was S3, so it's connected. And that's connected, so you go up by induction. Very good. Okay, that's very simple. Excellent. Okay. This Friday, I won't be able to give a lecture or have a problem session because I have a deadline for a paper. It has to be finished by Monday, so I have to work very hard next few days. But you might want to do a problem session on your own to discuss some. There are lots of problems we didn't do, right? Some are easy, some are harder. Maybe some that you did you found interesting. So I would suggest that maybe some of you get together on Friday and discuss some of those problems. Right? We can maybe talk about it after class today and see what you want to do. The usual time we meet, right? And then let me know which problems you did. So. You don't always need me there when you do problems. Then the week after that, I'm going to make up another lecture, and then the week after that, a problem session. Okay. Let me review what we did last time. So a couple of theorems. First, we said that G is nilpotent if I think we defined it to be upper GK inductively GK minus 1, and if GK is 0, then GK minus 1 is non-zero. Then we call it nilpotent, and the single solver if I let G lower k to be just the commutators of the commutators. And then I assume the same thing, that eventually I get 0, then I call it solver. There are several theorems. Let me first talk about nilpotent. Nilpotent implies that G is contained in the upper triangular matrices with 0 along the diagonals. So they're all subvalues of this for large n. And in fact, of course, the converse is also true. If it's subvalued here, it's certainly nilpotent. Another equivalent formulation was that ADEX is nilpotent. didn't quite prove that, but that's another useful way of looking at it. One way is clear, right? So if G looks like this, then when I take commutators, I go into smaller and smaller subspaces. Certainly, something in here, ADX is nilpotent. The converse is not very obvious that if this linear map is nilpotent for every x, that the leader is nilpotent is not quite obvious. I don't want to do that. Is there another one? G solvable. Was if and only if G is contained in the upper triangle matrices with possibly non-zero along the diagonal, which is clearly solvable algebra. Then we say that this is solvable if and only if G comma G is nilpotent. Which is kind of surprising, right? So nilpotent is solvable. So if this is nilpotent, certainly I get something solvable. So one direction is clear, but it looks like this is much stronger than solvable. It's not the same thing. Another equivalent formulation was that this is true if and only if the killing form be restricted to G comma G is 0. Okay. So that's another equivalent formulation. And I'm probably going to use that today, I think. Okay. Then we talked about semi-simple Lie algebras. That's what I want to continue today. Our main topics the next 2 weeks or so. There were several different formulations. G semi-simple if G has no abelian ideals. And that's if and only if G has no solver ideals. So this if and only if I didn't discuss, it's maybe an exercise. In one direction it's clear, right? An abelian ideal solver, so it has an abelian, it has a solver ideal, and the question mark is a converse. If it has a solver ideal, why does it have an abelian ideal? Maybe I'll leave that as an exercise. That's not hard. But you have to argue, it's not quite obvious. Right? And this was then if and only if what we call the radical is non-zero, which is the maximum solver ideal. Is not equal to 0. Okay, so I'm going to think of it this way. There are no abelian ideals. Something semi-simple, there are no abelian ideals. Particle, for example, implies right away that G is semi-simple. Pardon? Oh yes, if and only if maximum solver ideal is equal to 0. Yes. Grad G was a so the sum of two solver ideals was again a solver ideal. So there is a biggest one. That's we call the radical. If that's 0, then we call it semi-simple. So I think of it this way. It will be an ideal. Certainly G semi-simple implies a center of G is equal to 0. But that's not be an ideal center. So that's one thing that's clear. Another definition, G is called simple. If G has no ideals. Besides, of course, 0 and G itself. These are the trivial ideals. If you want to, you don't even count them. And I make the additional assumption that the dimension of G is not equal to 1. Certainly, one-dimensional Lie algebra has no abelian ideals. So by definition, it might be called simple, but that's not a good idea. Just exclude them. So the first result, I want to prove. Let's see. Equivalent formulation of being semi-simple, which is sometimes more useful. In fact, we want to use that can see that result frequently. G is semi-simple. If and only if the killing form B is non-degenerate. So we can express in terms of the killing form. And that we're going to use frequently later on. It's non-degenerate. It doesn't have to be positive or negative definite. Those are very special ones. So you can have a mixed signature. But at least it's non-degenerate. So for the proof, in fact, I'll reduce it to, say, a lemma or general statements about any Lie algebra. Not necessarily semi-simple. First is that kernel B is a solvable idea. B is next one. Three general statements. If A is a abelian idea, then A is contained in the kernel of B. So on every abelian idea, killing form vanishes. There was one more, maybe. No, I guess that's it. So I claim the lemma evenly applies the proposition. So let's see. Of course, so A implies one direction right here. This implies semi-simple, implies B non-degenerate. Right, because if it's degenerate, then kernel B is non-trivial. That's a solvable ideal, and that's not possible when it's semi-simple. B implies the other direction. Assume B is not degenerate, and there are no abelian ideals, then kernel B is trivial. That means there are no abelian ideals, and that was another way of saying it's semi-simple. Right, so this general lemma about Lie algebras in the killing form implies that right away. So let's maybe do at least a proof of A, so they're actually very close, very similar. So let's review something that we know about the killing form that we discussed earlier. We proved that at G is an isometry. For our G. So conjugation of X, Y isometries, if you want to. So it preserves the inner product, the bilinear form B. And this implies that at X is Q-symmetric. Because at X is a Lie algebra of at G, which I mentioned earlier, and the Lie algebra of an isometry consists of Q-symmetric matrices. What else did we prove? We proved that kernel B is an ideal. There's one more thing we proved. If A is an ideal, then the killing form of G restricted to A is simply the killing form of A in its own right. Because you remember also the definition was that so P of xy was trace of Rx of y. That was our definition. And these are three properties we discussed when we talked about killing forms. So, and this is the main property we're going to use here, that Rx is Q-symmetric. That's what makes it so useful, the killing form, that Rx is Q-symmetric. Almost all the applications use just that property, that Rx is Q-symmetric. So let's see. So So well, actually, A is very easy. You know kernel B is an ideal. So that means the killing form of A is simply a restriction of the killing form of G restricted to A. But A is a kernel, so that means BA is equal to 0. That implies that A is solvable. Remember, solvable was the equivalent formulation was that's if and only if the killing form, so G solvable, was if and only if the killing form restricted to the commutator is 0. So of course, if the killing form is dead 0, it's certainly solvable. So kernel B is a solvable idea. So that means that means A. B. Well, that's actually also very easy. Which I guess I don't have to use Q symmetry yet. That's the definition. B, A is abelian, so let's say E1 up to EK be a basis of A. And F1 up to FL, a basis, complete the basis. So F1 such that E1 up to EK, F1 up to FL is a basis of G. So let's take, what do you want to show? That the ideal lies in the kernel. So take X and Y in A. I want to show that ad X composed with ad Y is equal to 0. So what does it do? Where does it take A? Where does it take the subspace spanned by E1 up to EK, which is A? Well, this A was an ideal, so Y lies in A, so this lies in A again. Let's see. Oh, and it's abelian, right? So Lie brackets in A is equal to 0, so it certainly takes that to 0. Where does it take the rest? F1 up to FL. Well, so at Y, this is A is an ideal, so at Y takes it into E1 up to EK. And then ad X, if I compose after that, again takes it to 0. So this was an abelian ideal. So if you think of it as a block form, here's the basis E1 up to EK, F1 up to FL, then this composition takes the first ones to 0 and the second ones to the first ones. So that's the matrix of ad X at Y. So it traces 0. Okay, so it's actually very easy. So G is semi-simple if and only if B is not invariant. So the only thing that in here that we used, which was a little bit non-trivial, was that a Lie algebra with killing form 0 is solvable. That's produced in this step, and that's a little bit tricky. So now let's discuss the main property of semi-simple Lie algebras. Important property of semi-simple Lie algebras. So this lemma actually, since it's a general statement of the killing form, sorry, not clear. So proposition, G is semi-simple, implies that G is isomorphic to A1 plus AK, and where the AIs are simple, and the ideals in G. So I can write A in the sense of direct sum of Lie algebras just as a direct sum of simple ones. So to understand semi-simple Lie algebras, it's sufficient to understand simple ones. And that's what we're going to classify later on. So we classify all simple Lie algebras over the complex numbers. Proof is actually kind of nice. What do we know? We know B is non-degenerate. Right? That's what we're probably going to use for a semi-simple Lie algebra. And now we're going to use B non-degenerate and ADAX Q-symmetric to claim these arguments. So first 3 steps. If A is an idea, then A perp, which I define as a set of all x in G, with B x, y is equal to 0 for all y in A. So the Thorne complement with respect to this non-degenerate bilinear form. You have to be careful. B is not definite, so A perp could be A. Right? So clearly the form could vanish on A. So it's not necessarily a decomposition yet. Then part B is that A intersected A perp is trivial. So actually it is a decomposition in this special case, or same a simple one. And then part C is that A direct sum A perp is all of G. So let's maybe assume the lemma, assume these the effects and see how the theorem follows. So every ideal have a complementary ideal. That's what it says. So I can keep going. Right? So certainly I can say, well, by induction, G is a A1 up to AK, where AI are simple. Okay. So that applies that part of the proposition. I actually here want to make more claims. So certainly this is going to imply from this statement right here, just from C. Just induction from C right away. B is the decomposition is unique up to order. So of course I can change the factors, but that's the only thing I can do, since if B is a simple ideal in G, this implies that B is equal to AI for some I. So these are the only ideals, only simple ideals in G. So it's unique up to order. Maybe one more. Part 3, which will be very useful for us later on. Every derivation is inner. So in other words, derivation G is equal to Rx, where x and G is where the inner ones. So every derivation looks like this. Because what does that mean? That means that so I have a little bit more. So every derivation is and slightly stronger. Out G, what in G is finite. So certainly saying that every derivation is inner means that this Lie algebra, this Lie group out G and this Lie algebra in G have the same Lie algebra, which means that this one must be discrete in here. But it's actually finite. It's a little bit stronger than saying it's discrete. So that's an important property of semi-simple Lie algebras. So so this here was part 1. Let me see how part 2 follows. So from ABC. So B is simple. And all AI are simple. So let's intersect one of those. Let's take B intersected AI. Right? Intersections of two ideals is an ideal. So this is an ideal in B and AI. And both B and AI are simple, so E is trivial or everything. Right? So now there are a couple of possibilities. So one case would be B intersected AI is equal to AI. So this ideal in AI is all of AI. What does that mean? Then it also must, so that now this is also an ideal in B, right? It's not 0 because it's AI. So it means this must also be equal to B, because B is simple. So in other words, B is AI. So that's case alpha, that this is all of AI. Case beta would be it's trivial. For some I. So what does that mean? So if I look at, so these are components of a vector, and the ith component, there's no vector in B whose ith component vanishes. So let's look as follows. Let's take the projection of G into, let's see, we're taking element B here. It has sort of the form, say, x1 up to x, how many do we have? Xk. In using this decomposition. And this says that for each vector in B, let's see, what does it say? So nothing can be in AI completely. So if I look at this vector, then none where all the other components vanish. So do you want to go into AI? Do you want to go into AI or the rest? Let's try. Look at the projection onto the ith component. That's a homomorphism of the algebras, because this A was a direct sum of the AIs. Look at the ith components of homomorphism. So that takes B to AI. And this says what? By a vector, there are no vectors where all the others vanish. We want to go on to the rest. We'll try either way around. Let's maybe go to A1, like some AI deleted AK. That sends B into a subspace here. This injective. One of these must be injective, I claim. So you're going to have project. So if I B intersected AI is 0, if I delete the ith component, I never get something 0. So this means that the image, let's call this maybe projection of B, this is 1-to-1. So in other words, the projection from B into the image is 1-to-1. So what I want to claim, I think I'm being pretty stupid, what I claim is that B is contained in AI plus AI deleted plus AK. Right? Case alpha we concluded that B is AI. In the remaining case, I claim it lies in the rest. Which one should I use? This would say that the projection onto the ith factor is 0. Right? Maybe I should use this in here. If I look at the kernel of the homomorphism, projection onto the ith factor restricted to B, this is an ideal in B. Right. So if I go from B to the ith component, that's a homomorphism. Kernel is an ideal in B. B is simple, so it's 0 everything. So equal to 0 or B. Can it be 0? It can't be because this is 0. Right? If the kernel was 0, I'd like to say it's all of B, right? If it's all of B, it means that this is true. What does it mean if the projection is equal to 0?
You're done.
Because?
One of those kernels must not be trivial, because otherwise B will be 0.
If this is equal to 0, does that mean, does it contradict this? Is that what you're saying? I think that's what I'm trying to say.
No, I'm saying overall the indices, you must have one for which that kernel is not trivial, because otherwise B will always project to 0, and B will be 0. Why if that index,
okay.
and when I do that index,
So let me say it again. So what are you saying? There exists an I such that
the kernel of the projection I, when restricted to B, is not trivial.
is non-trivial. Okay.
I pick that I, and then I have the inclusion of B.
Correct. So then the kernel must be all of B, because the kernel is non-trivial, since B is simple. If it's all of B, it just means it lies in that component. Very good. So that's the way to say it. Okay. So that shows that this decomposition is unique. Every ideal B is AF for some I. Maybe I don't want to do 3. 3 is a little bit tricky. Let me leave that for you to read in the notes. So just maybe let me say a word what we do to prove C. So we look again at in G and out G. The other derivation G. And this was an inner derivation. We knew this was an ideal. Let's call this A. And then you show again that A perp is an ideal, and that the Lie algebra derivation of G is equal to A plus A perp. So you kind of repeat this argument I did here and observe that what I did there actually even also works in this setup. And then it follows easily. Maybe let me leave that out right now. Okay. A, B, and C, let me prove one of these just to see what kind of arguments are involved. So let's prove A. This may be typical. So now A is an ideal. What does it mean for A perp to be an ideal? It means I have to take an X in G and a Y in A perp. I need to show that the Lie bracket X, Y lies in A perp again. Now we can use non-degeneracy of the killing form B. So let's try to show that when I take X Lie bracket Y, take an inner product with anything in Z, so I claim for all Z in G, this is equal to 0. So why is that? I'm going to use skew symmetry of the Lie bracket. So if I interchange two of these, I have to pay with a minus sign. So let's switch these two, I think. So where does X Z lie? Oh no, maybe the other way around. Which one? Maybe X Z. X lies in G. Yeah, maybe let's choose Z and A. Then I could say that this lies in A, because A is an ideal, and Y was an A perp. So by definition, that's equal to 0. So it means that XY is orthogonal to A. Okay, so what does that mean? So that means XY is orthogonal to A, which means by definition it lies in A perp. That's what I want to show. G A perp lies in A perp. Okay, so that's a typical kind of argument to use with a killing. For use skew symmetry, and all these things follow easily. Here, for example, I can say now I know A and A perp is an ideal. The section of two ideals is an ideal, and use that property to take an inner product with any vector and show it 0, using the skew symmetry of ADX. And then if the inner product with everything is 0, by non-degeneracy, it must be 0 itself. And the last one is a general property of bilinear forms. So I don't know if you know this fact about bilinear forms. It's kind of a non-degenerate bilinear, so anything, right? So don't think of the killing form, doesn't matter. And if I have a subspace on a vector space V, say, if I take W inside a subspace of V, I take W perp with respect to this bilinear form. V is not necessarily a direct sum. You generally can't say that, but you can say that the dimension of W plus the dimension of W perp is the dimension of V. So at least they add up to the right dimension. They might intersect. They might even be the same thing, W and W perp. Then it has to be half the dimension. That's what this says. So this is a kind of a nice general fact about non-degenerate bilinear forms. So then if you have that, right, we know that a perp is an idea, they intersect, they add up to the whole dimension, then they must be a direct sum. That's how this follows. Okay.
And also the bracket restricts to provide some isomers.
Pardon?
Don't they, that's equality. It is as Lie algebras.
As Lie algebra, which means two vectors in here, you take the Lie algebra component wise, right? But I know A is an ideal, and A perp is an ideal. And so that means that if I take Lie brackets of x, y, and AB, it's just x A, y B, but that's what that equation means. And this is because by bilinearity, right? Say what is if x lies in A, y lies in A perp, the Lie bracket is 0. Right?
Yes, because of B.
So you should think of it as x plus y. So take the Lie bracket, that's probably a better way to look at it. X plus y in the product A plus B with respect to this decomposition. Right? Then, and now it's bilinearity. We'll break it apart, right? And XA, since I is an ideal, lies in A, and so on. So that's the way to look at it. Right, so this is a direct sum of ideals in that sense. Okay, so that's the first basic important property of semi-simple Lie algebras. I reduced it to the simple case, and in fact the decomposition is unique. Now I want to relate that to compact Lie groups. So I claim essentially G compact implies G semi-simple. So by the way, so maybe I didn't say this, a group is semi-simple if and only if the Lie algebra is semi-simple. A group is simple if and only if the Lie algebra is simple. Just like for nilpotent solvable, that's also how we define it there. The group is nilpotent if and only if the Lie algebra is nilpotent. And connected. So let me, yeah, okay. So G is simple if and only if G is connected. And the Lie algebra is simple, has no ideals. So it doesn't quite say that the G has enormous subgroups. It doesn't say that, right? So in the group sense, it may not be simple. But it says if it has a normal subgroup, it must be discrete. Right? Because it's the Lie algebra doesn't have any ideals. Right? So that's what it says. And that's the best way to define that. Properties of Lie groups which are simple in the algebra sense. I'm not sure what they all look like. Usually, Lie groups with simple algebra do have finite normal subgroups. Typically, the center is finite, for example. Okay. So we already saw here that this implies the center is trivial. I said this already. Because the center is an ideal. So So semi-simple Lie algebra has no center, but that means the center is finite. But almost all the Lie groups we saw have finite center. Right? So there weren't that many Lie groups we saw which didn't have a center. So that would be too strong a property, obviously. Then, but this it can't quite be true because as a counterexample, G is abelian. And the dimensions of the algebra, the dimension of group is bigger than 1. So that's certainly not symmetry. I think that's the only exception. So I want to show G compact implies that the Lie algebra G is a direct sum of the center plus another ideal A, so where A is a semi-simple ideal. So that's, you split up the center and then it's true. Then a compact group is semi-simple. And a little bit more than that. Let me see if I want to write it all down together. Not sure which one I want to prove first. No, we're not going to prove that first. So I'll come a little bit later. I'll probably finish that a little bit later today. But that's kind of the goal. I want to understand compact Lie groups. Eventually we're going to be able to classify compact Lie groups. And how do we do that? Well, we look at the Lie algebra. What kind of Lie algebra do compact Lie groups have? If it's a center, let's understand that. Let's split it up. That's not interesting. So assume it has no center. Well, then this is Lie algebra semi-simple. That means it's a product of simple ones. So I can understand compact Lie groups completely if I look at compact Lie groups whose Lie algebra is simple. So this reduces.
Of the center is a solvable ideal, right? General, for any algebra. Any algebra is the same.
Is a center plus something solvable? Is that what you said?
So a solvable plus a simple.
Yes.
In general,
Correct.
In the case of G is compact, the solvable is the center.
Is a center, exactly. The radical is the center. That's exactly what it says. Right. So let's reduce classification of G compact to G compact and simple. And that we're going to be able to classify. To understand that, we have to first prove something else. Here's a useful definition of what it means for a Lie algebra compact. So G is called compact if there exists a Lie group G which is compact and has Lie algebra G. So it's kind of cheating if you want to, but that's, I claim, is a good definition for practical purposes. So all Lie algebras of compact Lie groups are called a compact Lie algebra. Okay. Of course, that means an abelian Lie algebra is compact, because an abelian Lie algebra is the Lie algebra of a torus, which is compact. Right. So G abelian implies G compact. But essentially, that's the only thing essentially which is kind of silly. So there exists a compact Lie group. If you have a compact Lie group, you can average things. With a compact Lie group, I can average things. And this averaging procedure is something that's really useful. So A, let's look at I claim there exists an inner product, G compact. There exists an inner product such that at G symmetries, or at x plus q for all x. This is different from what I did earlier. The killing form has this property. Right? But now I'm talking about inner product. Inner product is positive definite. Killing form is not. But the killing form is probably never positive definite. It's sometimes negative definite, as we're going to see, but I think it's never positive definite. But this, so I'm talking about inner product. It's somewhat different from the killing form, but of course, we already saw that ADX being Q is very useful. I can use it all the time that ADX is Q. And now I'm even better shape because this is non-degenerate. This is positive definite and non-degenerate. Right? So there's no vector which has zero inner product with itself. So that's a much stronger property than the killing form. So that inner product is nice. Second one, there exists a metric on the legal G such that at G, or such that LG and RG are symmetries. So an inner product at every point of the legal G such that these left and right translations are symmetries. So then conjugation is also an isometry. And so then CG, which is LG composed with RG inverse, are isometries. Particular says that if I look at G, which was a derivative of this identity, they are symmetries of the identity. Right, so this also then applies again. G are symmetries. So such metrics are called bi-invariant. And whenever you have a bi-invariant metric, that's really nice to work with, both geometrically and also in many other contexts. And they always exist on compact Lie groups, on Lie groups with compact Lie algebras. So slightly more general than saying on compact Lie groups. Of course, slightly more general in the sense, in the silly sense, if you want to, that compact Lie algebra, the Lie group doesn't have to be compact, but then it's a Lie algebra of another compact Lie group, which is a torus. And then, of course, any inner product actually is Q because ADX is 0. Right? So that kind of exception of being a compact Lie algebra, shouldn't really bother you. So this is an average procedure, which you may have seen in other contexts already. So let me indicate. So for A, there exists the G compact with Lie algebra G. So we start with any inner product and average, with this being inner product on the Lie algebra. Then define a new inner product. It's called a 0. I take the integral of at gx at gy. Over the legal G. And so to multiply this with a volume form, so where omega is a volume for a bi-invariant volume form. So you may have seen this also in terms of Haar measure, right? A compact Lie group has a Haar measure, which is something bi-invariant. And you can use that measure to integrate. Right? But this is actually more elementary. You can just use some form which is bi-invariant. This exists is actually very easy. Multiply this function with this form, then integrate in the sense of forms. So differential forms. G is compact, so I can integrate in differential form over that compact group. And maybe you've seen this now. The claim is that when I do this, at GI isometries. Or of this new inner product. Kind of because they're average. That's kind of should be kind of obvious, but you have to write down a little bit. I take something that's not invariant, I average over something compact, it becomes invariant. So again, wrote write it down precisely. So this is isometries of this inner product. And then B, what do I have to do in B only? Well, I already have by part A some inner product at the identity, which were actually isometries. I move it around. So in part B is define an inner product on G with left translations. Right? So x, y at the point G, x, y in the tangent space at G, so I take L at G inverse. L G inverse takes G to identity. I pull the factor 4 at the identity, and then I take an inner product. So that defines an inner product on G. And then you prove that this new inner product on G is prime invariant. In fact, I already know it's left invariant. I define it as being left invariant. I push it around the whole legal. So I need to show that right and right translation are isometries. But I kind of know this already, right? If I'm actually conjugation isometries, at least at the identity. Okay. So I have a conjugation isometry, a left translation isometry, right translation isometries. Right. So again, that's kind of not surprising. And this is also, say, a general principle that one can use. See, in what general reality does this hold? It's a very general mathematical principle, I claim. So it takes any kind of object, whatever the mathematical object is. In our case, it was in a product, could be a differential form, could be a closure tensor, any kind of differential object on a manifold M, such that a legal G acts transitively on M. So every point is equivalent to any other point. And then I want to find a G-invariant object. So one where the left translations by G are preserve the object, right, in a product, whatever it is, right? So of course what you like to do is you start with a point, you want to push it around with left translations, right? So you fix a point P naught in M, and you define your object at the point P, in the product in the tangent space, tensor in the tangent space, whatever it is, differential form in the tangent space. And what do I need? And then I push it around. So, and define my object at phi as saying LG star inverse or whatever, of the object at P naught. I push it around the left translation. When is this? Because this is now invariant by definition. But it may not be well defined. You cannot take any object and define it at a point, move it down the left translation. That doesn't always work. What's the problem? That there may be a different left translation that goes from one point to the other. Right, so what do I need? I need that the object at P naught is invariant with isotropy. Do we call it G? Yeah. So these are group elements that fix the point. They must preserve the object. That means, and then I move on to less translation, and it doesn't depend on the point. So that's my completely general principle about homogeneous spaces. Defined at a point, invariant under the isotropy, then move it around, it's well defined as G invariant. So in this case here, this is a special case of this where the manifold is G, and the group G and I let the group G cross G act on G by left translations and right translations. And so in other words, take a point G, element G, comma H, let it act on an element, I don't know, K, and let's take a G, K, H inverse. So that's natural action of G cross G on the Lie group G. It's transitive, even left translation is transitive, even more than transitive, we have extra things. But that's actually useful. What is fixed at a point is precisely the conjugation. Conjugation fixed the entity. So if I want to use this action to move things around, what does it mean to be invariant under this action? Both left and right translation must preserve the object. Right? Not just left translations. Both left and right. That's what I want. That's how I choose this action. Well, for this to be well defined, I have to have that the points that fix this group element that fix the identity must preserve the object. And that's precisely conjugation. Conjugation is we make it invariant under conjugation. That's what we did in part A here. If I have a compact Lie group, I just average to make it invariant under conjugation. So in that sense, it's a really general principle that's quite useful. Okay. So to carry out this detail, that to prove that these things have these properties is kind of straightforward, but so I'm not going to write it down. Have you seen this before? Kind of. So now I can use this inner product to prove things about the compact Lie algebra. So I'm mainly going to use this Q symmetry over there. One is what I claimed earlier. If G is compact, this implies that G is equal to the center of G, plus, and I can even say what the rest is, plus G comma G, where G comma G is semi-simple. So just take all the commutators. That gets rid of the center. So you might expect that this is smaller than the rest. It's actually equal to the rest. And part B is G is compact if and only if G is compact with trivial center after all, by this result, those are the only interesting ones, right? Center, I might as well forget about. And trivial center, it looks like this. It's semi-simple. So it has this property if and only if the killing form is negative definite on the Lie algebra. So in particular, it says that if I take any Lie group such that on the Lie algebra the killing form is negative definite, then the Lie algebra has no center and it is compact. So it's Lie algebra or compact group. So only compact groups have this kind of property that killing form is negative definite. Because once you have that, that's actually quite useful because now I can choose minus the killing form as an inner product. So minus B is an inner product. And that's even a little bit stronger than saying have some inner product like that. So minus B is an inner product. And then part C, that's one. So these are actually not so difficult. Part C is difficult, and I'm going to write that down, maybe as a separate proposition. G, how do you want to formulate it? G compact and center of the linear algebra is equal to 0. G compact center of the algebra is equal to 0. This implies that every LIGO with the algebra G is compact. So we know by definition there is a compact one, but it doesn't matter which one we choose. They're all compact. That's the first part. And pi 1 of G is finite. And hence there are only finite many. Equals G with Lie algebra G. So in particular this property here that pi 1 of G is finite, which essentially that explains it, right? If pi 1 of G is finite, look at the universal cover, right? I already knew that the center of G is equal to 0, so the center is discrete. So that means the universal cover of G must have a finite center. That's what this sees. And I get all LIGOs by taking universal cover and dividing by a discrete subcover of the center. So that kind of implies this last part. So this here is a different part. Pi 1 of G is finite. You note that I give a geometric proof of the second proposition, which uses some geometry, and the theorem of Bonnet-Myers. I don't know how many people have had a course in invariant geometry where they've seen Bonnet-Myers. I'm sure you did, right? Anyone else? Two? Did you? Did you have a course in geometry? No? Okay. Did you? No. I can indicate a little bit the proof of this proposition, but I won't carry out the details then. But if you had a course in invariant geometry, and if you did DOCAMO, which probably is usually used here, right? There's an exercise in DOCAMO about bi-invariant metrics. Have you ever done that exercise? It's actually very nice. Okay, exercise as follows. Say G is a G is a LIGO. And I have an inner product on the Lie algebra such that at G are symmetries. Or equivalently, once I have this, of course, I know that I also have a bi-invariant metric on G. So hence exists bi-invariant metric. It's kind of the geometry of bi-invariant metrics, the main geometry of bi-invariant metrics. Then the first thing you show is that the connection is very simple. Connection is 1/2 the Lie bracket. So the algebra gives you the connection. The next exercise you show is that R, X, Y, Z, the curvature, is also given by Lie brackets. Think like this, maybe up to a sign, plus or minus this. Minus. Have you done that exercise? It gives you hints how to do it, right? It's not so hard. So that's the karma. Once you have that, I make the following observation that you may not have seen before. What do I get for the Ricci curvature now? once I know the section curvature like this. Well, let's do x comma x for simplicity. This is the trace of the map which takes a vector v into R of v x comma x. Depends on your sign now, the curvature tensor, whether you put it this way or this way. But anyway, if you take these vectors, you got it as linear map in one component, you take the trace, right? That's the vector tensor. Well, what is this now here? Y and Z. This is D bracket. So I think this here is minus ad x composed with ad x. Trace of that. So it's minus the killing form at x comma x. I probably have a factor wrong here, and this is probably, I think, 1/4 because of this 1/2 here. And here I get 1/4 then, and you get minus 1/4. Well, but what do we know about the killing form? Right, by this proposition here, which is easy to prove, we haven't done yet. B is negative in such a case, so minus B is positive. Right? So I have a metric with positive Ricci curvature. Well, now when minus says that this one is Paradas finite. So it's a nice application of geometry in the theory of Lie groups. This is usually called Weyl theorem, and it's not so easy to prove if you don't want to use any geometry, then it's hard. It's an important theorem in the theory of Lie algebra. Pi 1 is G finite. Okay. So if you haven't seen this, this is very easy to see in the notes. I won't do it. Maybe I explain this a little bit and how this gives you classification of compact Lie groups in a certain sense. And then I talk about the maximal torus of a compact Lie group and the Weyl group of a compact Lie group. That's an important concept for compact Lie groups is once I want to classify and study them, I use it as a simple case here. And then I take a maximal torus, and then I have a conjugation by the maximal torus. That defines me a Weyl group, and these objects give me some structure on the compact Lie to help me classify them. It's usually done often done on the Lie algebra level. Who took a course on Lie algebras here? I think someone was at you, right? So you often talk about the Weyl group or the Lie algebra. And how do you do that? You look at the Lie algebra, you look at a maximal Wien subalgebra, you define roots, right? Then you look at the subspace where the roots vanish, look at the reflections on those, and that's generally the group, and that's called the Weyl group. There's a much more geometric definition of that object if you work on the group level instead of the Lie algebra level. And that's what I want to do next time. Okay, which is next week, Monday. So try to maybe meet on Friday and discuss a couple of exercises. Let me know what you discussed and if you have any questions, and then we continue on Monday. Okay.